All right, everybody, we're going to get going now into section 3.7, which is the toughest one, I think, to date here in chapter 3. And this section is called the chain rule. And again, what we're trying to do here in the middle and towards the end of chapter 3 is learn how to take the derivatives of new styles of functions that we haven't really seen before. So obviously, you're looking at the rule here typed out already for you, but let's take just a minute and try to figure out what it is that we're attempting to accomplish here, because this isn't obvious, I don't think, as to when the chain rule actually applies. We are trying to take the derivative with respect to x, so remember that that's an operator, of this particular function right over here, f of g of x. And what I want you guys to recall, you've seen this notation over the last couple of years, but f of g of x is what we call a composition of two different functions. You might also have seen it with this notation right here, the f and then a little open circle in the middle of the line, and then the g of x. This right here on the right is the more traditional way of writing a composition of two functions here. This one on the left is a little bit more informal, but what I have found is that most people prefer that way of writing it there on the left because A, it's a little bit faster, but I think the real reason is it's more obvious what we're doing here in a composition function when we write it this way. If you were given two functions, f of x and g of x, and you were asked to do their composition, what you're going to do is take your x value, whatever that x value is, and plug it into the g of x function first. Then the output of g of x is going to become then the input into your f of x function. None of that is hugely important for what we're doing right now, guys, but what is important, and what a great number of AP Calculus students can get through the entire year and do very well on the AP test without ever really understanding, is that we use the chain rule when we're trying to take the derivative of the composition of two other functions. It's a very strange thing. A lot of people can do the chain rule and get these problems completely right. But if you were to ask them that simple question, well, when do you do the chain rule? On what kind of function? A lot of people aren't able to answer that, and they simply know it when they see it. But the answer to it is we use the chain rule when we're doing the derivative of a composition of two functions, f of g of x. So now let's move past the equal sign and move on to what's happening here on the right. You will notice then that the derivative we get by doing the chain rule is a product. And the first factor here we can simply read as f prime of g of x. Now let's take just a second and talk about what that means. You'll notice that g of x is the innermost function within this composition, and that g of x remains right here unchanged. But what's different is that the f, which was the outer function, that now gets differentiated. So we're taking the derivative of the outermost function first, but leaving the innermost function, the g of x, exactly the same. And that's a phrase you're going to hear me say a lot within this section, although you've already heard me say it a little bit earlier on in this chapter. The inner function stays the same. But at the end now, what we're now going to do is multiply that f prime of g of x by g prime of x. And g prime of x, of course, is the derivative just of that inner function there, g of x. So it's a little wordy right there. I'm going to erase some of this junk that I got in the way right here because it doesn't really help us to understand that at all. But that, everybody, is what the chain rule looks like. That the derivative with respect to x of f of g of x is equal to f prime of g of x, the derivative of the outer part with the same inner part, but then times the derivative within, or multiplied by the derivative of the innermost function. This slide right here is something that works pretty well when we're together in class as kind of an explanation for why or how the chain rule works, or why it's even necessary. But I think I'm going to skip this for right now and come back to it at the end of the notes in case you guys feel like learning a little bit more about it. But I would not say that what we are going to accomplish on this slide is absolutely necessary. Now, the good news about this section, guys, is that that one little formula that we just wrote down, that's it. In terms of theory, in terms of formulas. After this, I basically just have a series of 4 examples for you guys that show you how the chain rule can be used. So let's go ahead and dive into this. We're going to find the derivative of, in this particular problem, the function f of x, which is equal to 3x squared minus 7, and then quantity squared. So the first challenge right here for you guys is determining, first of all, is this a composition function? And if so, is it necessary then for us to use the chain rule? And the answer to that is going to be yes. And we're going to talk about why that is. The last thing happening in this function, if you were to think about order of operations, the last thing happening in this function is the square. So in essence, the first rule that I have to think about using is the power rule. I've got something, I'm just going to put a box around that for now, I've got something squared. So I have to consider, how do I take the derivative of something squared? And the answer to that is going to come from the power rule. But what's inside that set of parentheses, the base of the exponent 2, that 3x squared minus 7 has a derivative in and of itself that needs to be considered as well. So what I'm going to do right here is really not something we're going to do on a great many problems here, but what's kind of going on here is that we've got two different functions. Now I've already called this f of x, so I'm not going to be able to use the exact same notation that I did here on slide number 1 where we were using f of g, but what I'm going to do instead is I'm going to talk about g of x. I don't like where I put that. That's fine. G of x being the outer function. And then we're going to go h of x being the inner function. And again, this is not something you guys are going to do most of the time, but just something that we're going to have to get used to here at the beginning. Now, I think the inner function is probably easier to see because when you hear or say or read the in of inner, you automatically think inside. And parentheses provide a really nice structure. The inner function here, the h of x, is going to be the 3x squared minus 7. That's inside the parentheses. That is the base of that exponent. And now the outer function, what is happening to the 3x squared minus 7? It's being squared. But what some people get right away and some people need a little bit of work on is that the outer function then is simply going to be x squared. And what's going on, again, you don't need to write this out here, guys, but that f of x is equal to the composition of h of x being your inner function plugged in for x in this function. So the way we've written this out, f of x is really defined as g of h of x. H of x, the 3x squared minus 7, is the inner function. So this is really g of 3x squared minus 7. And g tells me to take whatever my input value is and square it. So the input value here is 3x squared minus 7 quantity squared. Now, we haven't done anything, you guys, in terms of derivatives yet. This is really just a way of rewriting this problem and trying to understand that f of x is, in fact, a composition of two other functions. So as fun as that was, I'm going to undo a lot of what we have written right here, but I do think it would probably be worthwhile to keep these two tidbits of info right here. Not necessarily that we're going to need it, but all right, the outer and the inner. So now that we've established that f of x is a composition function, now we know the chain rule applies. And the derivative of f of x, that's what's going on right here, is equal to f prime of g of x. That's the derivative of the outer function, and the inner function stays the same. But then at the end, we multiply by the derivative of the inner function. So in this problem here, in f of x, we are trying to find now f prime of x, and here's how we do it. We take the derivative of the outer function first. And the derivative of x squared, you're going to be tempted to say is 2x, and you're going to be tempted to write that. That is not really the way we want to look at it. What I would really advise you start doing, and as silly as this sounds, say the words out loud. G of something is something squared. Try to make yourself say the word something rather than the variable x. So the derivative of anything squared is 2 times the same base, and now of course it's technically being taken to the first power. This is really the power rule in effect. The derivative of some base squared is 2 times the same base, and we lower the power by 1. But as you heard me say a while ago, whatever the base was, or in this case whatever the inner function was, that remains unchanged now. So the base of that exponent was 3x squared minus 7. It's still 3x squared minus 7. So this is what it means, guys, when we take f prime of g of x. Okay, but then at the end of all that now, we're going to multiply here by g prime of x, which was the derivative of that inner function that we didn't change. And the inner function here, h of x, was 3x squared minus 7. So the derivative of that is going to be 6x. So obviously we can clean this up just a little bit. That exponent of 1 obviously doesn't need to be there, but we've got a 2 and a 6x being multiplied together, so I definitely think we should make that a 12x multiplied by the binomial of 3x squared minus 7. And now there is one other thing that we could do. We could distribute the 12x in there. Clearly, that's within the realm of reason. It's not all that difficult to do, but honestly, guys, it doesn't do a whole lot for us. All right, so it's perfectly fine if you want to go ahead and distribute that 12x in there, but I think that either one of these forms of the final answer here would be acceptable. I don't know that the second one is necessarily simpler than the first one. So either one of those could be our answer. Now, you guys know, I hope by now, that I very often like to start you off with an example that actually can be verified in a different way. We did this problem using the chain rule because it was written as a composition. But I did want to start off with a relatively simple one because the original expression here, I don't know if you guys thought about this when you saw it, can be expanded. And then we can find the derivative a second way. And if we've done this right, we should end up with the same derivative again. Now, some of you guys goofed this up on your last quiz. What I'm doing right here, you guys, is I'm not taking the derivative yet. I'm just rewriting this thing as f of x. And another way of rewriting 3x squared minus 7 quantity squared would be by squaring the binomial. So my a squared term, the 3x squared squared, is going to be, hand got in the way again. All right, is going to be 9x to the fourth. Then it's 3x squared times a negative 7, which is a negative 21x squared, doubled. That's a negative 42x squared. And then at the end, it's a plus b squared, and that's going to be a plus 49. So again, that's not calculus at all, guys. That's just rewriting the original function, f of x, in a slightly different manner. But now you will notice that in that particular expression of the function, 9x to the fourth minus 42x squared plus 49, that, everybody, is fully expanded. And so to take the derivative of this form right here doesn't require any magic tricks. So if I was going to think about f of x looking like that, then f prime of x would simply be, well, let's see, using the power rule, the derivative of 9x to the fourth would be 36x cubed. The derivative of a minus 42x squared would be minus 84x, and the derivative of that constant, 49, is non-existent. It's 0. So here's the derivative you got if you expanded the original function, which I think you will notice equals the derivative that we got right here by using the chain rule. So what I think that illustrates there, everybody, is that the chain rule does in fact work. If you can express the original function in two different ways, and take its derivative then in two different ways, but end up with the exact same answer both ways that you do it, that lends a lot of credence to the idea that we're doing this problem correctly. Okay, so that's our first example with the chain rule. Let's move on to another one here. Now, in this one, we're kind of moving away from polynomial functions, and now we're getting into a trigonometric function. So, where's the composition here? The inside part of the parentheses here, the 3x minus pi, which of course is the angle that we're taking the cosine of, that becomes your inner function. And the cosine then becomes the outer function. All right, and for some reason, just to give you some mental exercise, I decided to call this thing q of x. So we could write it now as the inner and the outer function, but we're not going to be doing that very often, so I kind of want to transition right away now into you guys just being able to see what's what. So if that's q of x, we're going to write now q prime of x, the derivative of q, and here we go. We start off always by taking the derivative of the outer function, while leaving the inner function alone. So the outer function is cosine. So what you should be asking yourself in these exact words is, what is the derivative of cosine of any angle? And the derivative of cosine of any angle is the opposite of sine, but this becomes really important now, you guys, of the exact same angle. And that's why I made a point of saying in the 3.6 notes that I want you guys to remember the angles and not just say to yourself the derivative of cosine is negative sine. Okay, or that tangent is equal to sine over cosine. I know it sounds nerdy, I know it seems unnecessary, but it does help you stay mentally organized to say this properly, that the derivative of cosine of any angle is equal to the opposite of the sine of the exact same angle, which again is going to be 3x minus pi. So there's the g prime, or excuse me, there's the f prime, everybody, the derivative of the outer function. And there's the g of x, the inner function stayed exactly the same. But wait, there's more. Chain rule says that we now multiply all this times the derivative of the inner function. That's the g prime of x. And 3x minus pi, remember guys, the variable here is x. The pi is just a constant. So that's a linear function, and the derivative of that is just its coefficient, which is 3. And obviously that can be rewritten just a little bit right here. It probably would be better to move the 3 out in front. So I think we'd make that a negative 3 times the sine of the exact same angle we started with, which is going to be 3x minus pi. And that, again, is a phrase you guys are going to hear me say a lot, and you should be saying it too. The angle never changes. I'll say it again. You try to do it too. The angle never changes. The angle we were taking the cosine of here was 3x minus pi. Well, that's the same angle that we're taking the sine of here at the end. The angle never changes. And the more you can say that to yourself and say it out loud, the better that's going to sink in. Okay, so that's what the chain rule looks like when we're doing a trigonometric function. How about one like this? Okay, h of x is given to us now as the square root of 3x cubed plus 5x minus 2. Well, probably the best thing to do here before we go any further, and guys, I've been doing calculus and derivatives since a long time, since about 1994, and I still, to this day, if I'm taking the derivative of a radical, I usually find it easier and a much better strategy to rewrite this with a fractional exponent, to make it 3x cubed plus 5x minus 2 and raise all of that to the 1/2 power. There are certainly ways that you guys can memorize for how to take the derivative of a square root, but just kind of let that happen naturally and let's not try to force it. So we're going to differentiate this version here instead. And actually, what we have here, a base raised to a power, is a lot then like the problem that we did here in example A, taking the derivative of a function that was a polynomial base, in this case 3x squared minus 7, raised to a power which was 2. Well, here, your polynomial base is 3x cubed plus 5x minus 2, but it's being taken to the 1/2 power. So here we go, guys. H prime of x then. We start off by taking the derivative of the outer part of the function. And the last thing happening in this function is the 1/2 power. So how do we take the derivative of something to the 1/2 power? We go ahead and we apply the power rule. We bring the exponent out in front, or the old exponent I should say, to become a coefficient. So it's 1/2. Here's the most important part. The base remains the same. That's going to stay a 3x cubed plus 5x minus 2. Now we drop that exponent by 1, and 1/2 minus 1 is going to get us a negative 1/2. So that's the power rule. That's the derivative of the outer part. That's the f prime of g of x, but the base stayed the same. And now we multiply that at the end now by the derivative within, or the derivative of that innermost function, the base. And that derivative is going to be a binomial. That's going to be a 9x squared and a plus 5. And I think everybody knows this, but a lot of us think we know it so well that we don't need to bother writing it, and then we end up making mistakes. Make sure you put parentheses around any polynomial. I didn't do that on the last problem. My derivative within was just a monomial of 3, so it wasn't necessary. But anytime you've got 2 or more terms, we really do need to have parentheses around that. Now, that right there is the end of the derivative. That's h prime. So we're going to get most of the points here already just for getting to that spot. But one of the things you guys have heard me say is to simplify as much as is reasonable, and going along with that, to try to get the format of your answer to match the format of the original function, which is right here. And you'll notice that when h of x was given to us, it was given to us using a radical, not with a fractional exponent. So I think it would be worth our time to take a moment here and try to write this maybe in a better way. All right, the first thing I see is a 1/2. That 1/2 is going to show up as a 2 on the bottom. The 3x cubed plus 5x minus 2 is being taken to a negative 1/2 power. The 1/2 means it's going to be a square root, and the negative means we're going to put that square root on the bottom of this fraction. But the radicand stays the same, 3x cubed plus 5x and a minus 2. And the last thing to deal with is the 9x squared plus 5. That factor just gets multiplied in the numerator, doesn't have anything to get multiplied by, so it just stays 9x squared plus 5. And that, everybody, is about as good as it's going to get. The one thing I could have done, maybe should have done, humor me for just a second, if, just for the sake of argument, that was an 8x squared, and this right here was a 6, now I would notice, as I think you guys know where I'm going here, an even number here of 8, an even number here of 6, and an even number here of 2. We could cancel that out. And in that case, I would make this a 4x squared plus 3, and now the 2 on the bottom is just gone, and I'd leave the square root right there. So that does happen in some problems, but as it is right here, 9 and 5 were not both divisible by 2. In fact, neither one was divisible by 2. And so for that reason then, this answer that we have right here is as good as this one's going to get, and that's h prime of x. Okay, moving right along here. So we've seen now 3 different styles of composition functions. This one was strictly polynomial, a polynomial base to a power. Here we had a trig function. It was the angle of a particular function. And in the third one here, it was a radical function. So we were taking the square root of a polynomial. And then there's this mess right over here. This will be the last one that we do here today, guys. J of x is equal to tangent to the 5th of 3x. So if I were to ask you guys what's happening right here to your variable x, well, the first thing going on right here is that x is being multiplied by 3. So that 3x right there is really your innermost function. Then the question becomes, what happens to the 3x? And here's where you've got to slow your roll just a little bit and remember what it means to have an exponent on a trigonometric ratio. The next thing happening here is that we'd be taking the tangent of that particular angle here. Now again, if I was doing this with compositions, I would just call that an x for right now. And now maybe you see where this is going. After you've taken the tangent of the angle, the last thing that happens to evaluate j of x is to take the tangent of 3x to the 5th power. So x to the 5th is actually your outermost function. And if you guys haven't figured this out, this is now going to be a 3-part composition, which means the chain rule is going to get much more complex here than it was before. Okay, before we go any further, I think it again would be a good idea just to rewrite the original function in a manner that's going to help us a little bit more. I'm going to move that 5th power out to the outside here and make this tangent of 3x, close the parenthesis and close the bracket, and take all of that to the 5th. And I really think that if you write it that way, it is going to be more clear to us now what happened last, what happened in the middle, and what happened first. So I think we're ready to get started here, guys, trying to find j prime of x. Okay, so you want to ask yourself this question. What is the last thing happening here in this function? And the answer to that is the 5th power. So the first rule we've got to think about is, how do we take the derivative of something to the 5th power? This is really the power rule. And the way we do that is by bringing the exponent out in front and making this a 5. Now the base doesn't change at all. The base is still going to remain the tangent of 3x. And that exponent drops by 1 from 5 down to 4. So what we have right here, everybody, if we went back to the very first slide, what we have right here is f prime of g of x, but the g of x, the base of the exponent, didn't change at all. Now, we have to multiply all of this by the derivative of that base. And I'm going to use some colors right here, guys. The base itself is the tangent of 3 of x. And we now need to take the derivative of tangent of 3 of x and multiply it by what we've already come up with. So let's talk about that. How do we take the derivative of tangent, now use the words right, tangent of an angle? So going back to 3.6, the derivative of the tangent of any angle is equal to the secant squared of the same angle. That's the secant squared of 3x. But wait, there's more. Just like we dealt with right back over here in example B, when you go to take the derivative of cosine of an angle, you do the derivative of cosine, which is negative sine of the same angle, times the derivative of the angle itself. So back over here, guys, I now need a third color here. The angle itself is 3x. We now need to take the derivative of 3x and multiply that by the secant squared of 3x. And the derivative of that 3x is just going to be 3. So we really had to do right here the chain rule within the chain rule. And the reason why is because this was actually a 3-part function here. This one had 3 different functions being composed, as opposed to the ones we've done before, which have all been 2. And that is something, you guys, that is going to take a lot of practice. It's something that confuses people when they look at here. And even if you think you get it right now, we probably need a little bit more time working on that. Okay, now, the good news is all the calculus is done. Now we just need to clean up this whole mess right here, so let's see what we can come up with. J prime of x then would equal, what would be best if we brought it out in front? Well, we've got a 5 for a coefficient, and the only other constant factor is a 3. So we'll go ahead and multiply those and make a 15 out in front. At that point, I still have to worry about this, and I still have to worry about this, and I think probably the best way to write it, again, trying to match the format of the original expression, would be 15 tangent to the 4th of the angle, 3x, multiplied by the secant squared of that angle, which again is 3x. And I said it 2 examples ago, and I'll say it right now, the angle never changes. We started off here with an angle of 3x, and sure enough, that's the angle here and here. And that, guys, is as good a job as we can do of simplifying that expression here for j prime of x. So that's going to take a little bit of time. Tangent times secant, I don't think does anything for us. Tangent, of course, is sine over cosine. Secant is 1 over cosine. If these 2 cosines were on opposite sides of a fraction, you know, one was on top and one was on bottom, then they might cancel each other out. But with them both being on bottom, I don't think there's any benefit to rewriting this. I'm pretty happy with this answer here, the way that it's written. Okay, guys, so those are all the examples that I wanted to do with you here in this section. I did say I'd go back to slide number 2 and talk about this quickly. So if you feel like watching this, great. And if you don't and you want to turn the video off now and just get to the homework, I get it. But if you guys can see what's going on right here, this really looks like a sine wave. Passes through the origin, has a max value of 1 and a min value of -1. The only big difference is that the period of this sine wave, everybody, well, let's take a look. This thing starts at 0 and completes 1 full cycle right over here at pi. That's interesting. The period of this sine wave here is pi, whereas normally that period is 2 pi. Guys, the graph that we are actually dealing with here is y equals not just the sine of x, but rather the sine of 2x. And if you guys remember your period, I don't need to write this down now, but your period for a sine wave was going to be the normal period, 2 pi, divided by b. That number right there is your b value. So in this case, that ends up being 2 pi over 2, which just equals pi, and that matches what we saw from the graph. All right, let me get rid of some of that junk at the end right there. So again, what we're looking at in red there, you guys, that curve is the sine of 2x. And at the beginning of this section, everybody, let's keep it there. Before we started talking at all about the chain rule, if I asked you guys what the derivative of sine of 2x probably would have been, you guys probably would have said that the derivative of sine of an angle is equal to the cosine, hopefully you would have said, of the same angle. And you'd think you were done and go on your merry way. Well, what I wanted to do with this, and the reason I used the calculator to graph this so properly, is I wanted to talk about what it looks like if you were to draw a tangent line right here. And what I was hoping you guys would notice is that this tangent line looks an awful lot like that. I didn't draw it very well, but okay. And I was going to ask you guys then to take a guess here as to the slope of that particular tangent. Well, what I was hoping you would see is that from here to this point right over here is a rise of 2 and a run of 1. The slope of that tangent is 2. Now, if we were right with our initial guess right here that y prime would equal cosine of 2x, then y prime evaluated at 0 would be the cosine of 2 times 0, which is 0, and that would equal 1. That would need to be the slope of that green tangent line. But pretty clearly, it's not. Okay, the slope of that tangent, if I had drawn that right there from here with a slope of 1, that line would have looked something like this. And I think you guys can see right away something doesn't look right there. That purple line is not tangent to the original curve passing through the origin. So the purpose of that exercise was just for you guys to realize that simply taking the derivative of sine of an angle to be cosine of the same angle doesn't get you the right slope of the tangent, and therefore it's not the right derivative. Now, the question I was going to ask next was, what should the slope of that tangent be? And the answer to that, back to the green line, it really should be 2. So then I was going to ask you, what do you need to do now to the cosine of 2x so that when you put in a 0, you do end up with a 2 instead of a 1? And then at that point, a lot of people say, oh yeah, you just need to multiply that by 2. Well, that's the concept that we've just been talking about now, guys, kind of doing all this backwards. If that was y, then y prime would equal, let's see, the derivative of sine of any angle would be cosine of the same angle, 2x, times the derivative of that angle, which would put a 2 out in front. That, everybody, is the derivative of y prime. And now, if we were to evaluate y prime at 0, okay, basically the slope of that green tangent, this becomes a 2 times the cosine of 0, which is 1, which equals 2, and that's what it probably should be. So that was meant just to be a little bit of an introduction right here to the need for the chain rule and the fact that you can't just put your head down and plow through this the way that you normally would. Okay, that's probably enough for that. I think you guys should get started in 3.7. As I said, it's nice in that there's really only one concept, but being able to actually use that concept effectively, that's going to take some practice. So good luck on the homework, guys, and let me know if you have any questions.